Welcome back once again. We will continue discussing the basis of approximations in engineering. Here again, we will do more examples to learn to make and justify approximations in engineering sciences. In the last lecture, we have said that in order to establish which terms in the governing equation are negligible, their magnitudes need to be estimated. And one very powerful method of making such estimates is to normalize each variable by scaling it with its characteristic value. If the characterizing values of the quantities are chosen properly, the normalized variables are then expected to be order unity. That is, except at certain isolated points in the flow field, the values of the transformed variables are expected to be neither very large nor very small compared to unity. Further, it is hoped that the dimensionless derivatives of the various physical quantities appearing in the equations are also of order 1. And we saw that in well-behaved function this is possible, but sometimes this breaks down and the approximations or the estimates obtained are erroneous. We will learn to deal with this situation in a later lecture. If the proper estimates are obtained, then the coefficient of the various terms reflect the estimate of the corresponding term in the equation. Based on these estimates, we can then decide what terms can be neglected. We have been doing this for 2 examples that we discussed in the last class. But life is never easy. There are pitfalls on the way. Be on the lookout. We had seen one pitfall when we discussed the large Reynolds number flows. We start with a simple example of a damped oscillator. The equation for a damped oscillator is this. The first term represents the inertial terms, mass times acceleration. The second is the damping term, the damping coefficient C times the velocity is the damping force, and Kx is the spring force. So these 3 forces sum out to 0 as there is no external force applied to the system. We start with a very simple boundary condition that time t is equal to 0, the displacement x naught and the velocity is 0 at time t is equal to 0. We normalize the dependent variable x with its characteristic value xc, and we normalize time with a characteristic time tc. And this is what we obtain. And if we make the coefficient of the first term, that is the inertial term 1, then this is the form that we get. This is an estimate of the viscous force, and this is the estimate of the spring force, provided that we have taken x, c and tc appropriately. That is, they are indeed characteristic of the system. The boundary conditions become x star at t star is equal to 0 is 1 and x dot star at t star is equal to 0 is 0. I have copied those equations here. If we solve this equation, and it is easy to solve, this is the kind of variation that we see of x star with t star. This term, recall that we have not chosen t star yet. We said only that tc is the characteristic time. But what is its value? Now, if this mass is to oscillate, then the spring force must be present. The coefficient of inertia term is 1. So this term to be present means that this coefficient should be of order 1. And if this is of order 1, then this suggests that Tc may be chosen as under root m by k without any loss of generality. This is a characteristic time in this problem. We will go further than this. We introduce a symbol omega n as 1 over Tc, it is under root k by m. This at times is called the resonant frequency of an undamped oscillator of mass m with a spring constant k. From a high school physics, you must recognize the resonant frequency. So in terms of omega n, the equation now reduces to this. This was the original equation where we had chosen this to be 1. We could have also used this for defining Tc, the characteristic time. And if we did this, we will get characteristic time order of m by c rather than m by k under the root. We will get it as m by c. So there really are 2 time scales in this problem. One time scale under root m by k and the other time scale m by c. What is the meaning of these 2 time scales? This is when c is less than under root twice mk. This is the blue line is the variation of x star with the t star when c is less than 2 under root mk. That is when this time is much more than this time. This is a shorter time and we get these fluctuations of x star, the vibrations of the oscillator at the frequency that is suggested by under root m by k. But when this time is less, that is when c is greater than 2 under root mk, then the red line represents the solution. It is no longer oscillating. So this is when this characteristic time dominates, it is a lower value. So damping takes over before the vibrations take place. And this line is what is called the critical damping. This separates the 2 domains. The original equation again. If we look at the first case where the time scale is under root m by k, then we get these solutions. The exact solution of this equation, x star is equal to twice e raised to power minus c divided by twice under root mk, t star cosine omega over n, t star plus phi. Notice that in this solution, both the time scales are present. This curve that marks the envelope of the amplitude has the time scale of this under root mk, c by under root mk. So this time scale is for the damping of the amplitude. And This time scale, under root m by k, is the time scale for the vibrations per se, these vibrations. This is repeating the information from the last slide. Now let us consider c by under root mk much less than 1. That is this much less than 1. If this is much less than 1, then we can drop this. This term can be dropped from the equation. And the equation reduces to x star double dot plus x star is equal to 0. The equation for simple harmonic motion, whose solution is x star is equal to cosine t star, with the boundary conditions that were given, that x star is equal to 1 at time t is equal to 0, and that x dot star is 0 at the initial time. When c by 2 under root mk is much less than 1, this approximation, simple harmonic motion, is a very good approximation for any one cycle. But if we consider many cycles, that is for very large t star, the agreements become very poor. Initially, this picture and this picture for very small time may be same, but for large times, the second picture is entirely different from the first picture. The difficulty is that though this is small, the viscous term is small, but now it is acting over a very large time. This is small, but T star is becoming very large. And when the T star becomes very large compared to 1, such that this no longer is small, then the approximation breaks down. So the effect of this viscosity integrated over a large time gives a large effect. So we need to worry about this while making approximations. A problem like this that behaves like this is said to be singular in its limiting behavior. For example, here for time t star very large, that is, the behavior of the solution when a parameter is very small is altogether different from when the parameter is identically 0. When we dropped this term, the viscous damping was assumed to be 0. But actually it is not 0, it is small, the coefficient is small. So the behavior of the solution when the parameter is very small is altogether different from when the parameter is identically 0. This is the behavior when the parameter is identically 0, and this is the behavior when the parameter is very small. They are entirely different. This is called singular behavior. When singular behavior in the limit occurs, we usually try to resolve the difficulty by expanding in the powers of that parameter, so that this equation is written like this, where this term is replaced by epsilon. Epsilon is small. Now we obtain a series solution of this equation. We assume that x star is equal to x naught plus x naught star plus epsilon x1 star plus epsilon square x2 star plus so on. we plug this x star into this equation and then set equal to 0 and then get a series of equations by equating the coefficients of epsilon and epsilon square, epsilon cube separately. So the equation when we drop this term results when we take only this, not this. This solution is perturbed by this and this to a higher order. We'll do an example of this a little later. Let's look at undamped oscillator in a little more details to understand what we do when we make approximations. This is the undamped vibrator with the initial conditions that at time t is equal to 0, x is equal to x naught, and x dot is u naught. Earlier we had taken x dot to be 0 at time t is equal to 0. Now we assume there is an initial velocity u as well. The complete solution with these cases is this. This equation is not difficult to solve and we can solve this. This is easy to solve. Now if we normalize this equation, what is the characteristic value of x that we choose? Do we choose this, x naught, or do we choose this? In fact, neither of them is satisfactory for the full range of x naught and u naught. Instead, xc is equal to under the root x naught squared plus u naught by omega n whole squared is the most suitable choice. But it is not easy to see. It is only after we have worked with the solution, get stuck, that we realize that if we choose this, then we get the best results. Let us choose a characteristic time tc arbitrarily as tau. The equation and the boundary conditions become x star double dot plus k tau square divided by m, x star is equal to 0, with x star is equal to x naught by xc that we defined earlier, and x dot star is equal to u naught tau by xc. Now let us consider the case when k tau star by m is much less than 1. If this is less than 1, this term drops out and we get x star double dot is equal to 0. A trivial equation. Double integration and use of the two boundary conditions give you this value as the solution, which matches with the exact solution x star is equal to cosine omega n tau t star plus u naught divided by xc omega n sine omega n tau t star for small values of omega n tau t star, but deviates more and more as t star increases. The same problem as we begin. For very small t star, it is valid. To increase the range, we'll have to use a series solution with k tau square by m is equal to epsilon as a small parameter. However, when k tau star by m is much greater than 1, the first term, the inertia term drops and the only term that we get left with is x star, and so x star is 0. And now we cannot even match the boundary conditions. We have no solution at all unless the boundary condition is trivial. It's exactly like what we did earlier. For small value of k tau star by m, we have a solution which is valid for small values of tau. But when k tau star by m is much greater than 1, we have no solution at all. This is much like the boundary layer of Prandtl. This is much like the high Reynolds number flow where we cannot satisfy the boundaries. And a similar solution would be in order. This type of difficulty often occurs whenever we try to drop the highest order term. In such cases, we can no longer satisfy all the boundary conditions, and we can therefore obtain solutions only for a certain very limited values of boundary data. This type of difficulty can sometimes be resolved by various kinds of expansion in powers of the parameter or by a technique which we call boundary layer theory. We will come to that later in the course. Now, after this discussion, let's do a very simple example. Let us consider determining the time required to prepare perfect baked potatoes in a convective oven. Let's, for the purpose of simplification, consider the potatoes to be spherical of radius r. Initially, this black line represents the temperature. This is the initial temperature T naught throughout the potato. Temperature Tf is the temperature in the oven. The air in the oven is temperature Tf and is heating the potato by convection. Then after a little time, the temperature profile may look like this. The temperature at the surface would increase. There will be variation of temperature within the potato. At a very small time, the center of the potato may still be at temperature T naught, and the temperature in the boundary layer around the potato would look like this. At a little larger time, the temperature at the center would also start rising. Temperature everywhere in the potato was rising, and this might be a profile, and still a later time, the profile may be this. Let the initial temperature of potato be T naught, and let it be placed within a convective oven at a temperature Tf. Let us say that the potato is considered perfectly baked if every part of it is held at a temperature Td, the final temperature, for at least a time small td seconds. Then the time to bake the potato would be time to bring the center point, which is the coolest, to the temperature Td plus this Td. The sum of two times would be the time required for baking the potatoes. The unsteady heat transfer equation in spherical coordinates that you would have studied in a course in heat transfer is this. This term represents the heat that increases, or the quantity of energy, the thermal energy that increases within the potato, and this represents the heat that is being conducted at the surface of the potato into the potato mass. This equation is to be solved subject to the initial boundary conditions, that T is equal to T naught for all values of R for T less than 0, the initial temperature of the potato, and then at the surface of the potato, the heat conducted into the potato, which is minus Kf del T by del R at R is equal to capital R by Fourier law, is equal to H times T minus Tf, the instantaneous temperature minus Tf, or the other way around, Tf minus T. My negative sign will take care of that. This is the convective. The conductive flux at the surface is equal to conductive flux. Or, I'll say that sentence again, the conductive flux is equal to the convective flux. We normalize the variables by defining a normalized temperature difference. T minus T reference we choose as Tf, divided by T naught minus Tf, the initial temperature difference, the characteristic temperature difference. And R star is equal to R by capital R, and tau star is T by Tc, a characteristic time. We, as yet unknown, will try to determine what the Tc should be from the equations. And if we normalize the equation, this is what we get. And by making the coefficient of the first term as 1, this is the coefficient that we get here. We presume that this is of order 1 and this is of order 1, a regular behavior. So this measures the importance of the convective term. The initial and the boundary condition change to theta star for all values of R star is 0 at time t is equal to 0, and the convective boundary conditions becomes delta theta star by delta star is equal to HR by Kf into theta star at R star is equal to 1. Two parameters, one is Ks Tc divided by rho C R square, and using alpha, the thermal diffusivity, for K divided by rho C, the properties of potato. So alpha is the thermal diffusivity of potato. Alpha Tc by R square is a term that we came across earlier, and we had named it there Fourier number, Fo. And we get this other parameter, which is termed as Bayer number, HR by Kf. H is the heat transfer coefficient in the fluid, R is the radius of the potato, and Kf is the thermal conductivity of the fluid. Notice that in Fourier number, it is thermal conductivity of the solid, and in Bayer number is the thermal conductivity of the fluid. So this is what the equation looked like after we inserted Fourier number and Bayer number in the equations. So this will give you theta is a function of R star, Fourier number and Bayer number. We are interested in the center line temperature. For center line, R star is 0. So theta center line is function of Fourier number and Bayer number. And we have seen before that it is given by Heisler chart. This is theta, the non-dimensional normalized temperature of the center line. This is the time variable Fourier number, and there are different curves for different Bayer numbers, so 1 over Bayer number is used as a parameter. If we determine what is the theta that we need, we go to the relevant Bayer number curve, and from this we read what is the Fourier number that we want. And this would then, from this we can calculate what is the time that would be needed to get the temperature to the required temperature. We had earlier discussed that we could find the temperature at any other point by using what are called the position correction chart, which gives you the non-dimensional temperature difference, divided by the non-dimensional temperature difference at the center line, the ratio, as a function of 1 over Bayer number with the location as a parameter. So this is for the center line, the ratio is 1, and at x star is equal to 0.2, it would be this, x star is equal to 0.4, it would be this, and at the surface where x star is 1, this curve would be this. Interesting thing to note is that for 1 over Bayer number large, that is a Bayer number small, there is very little temperature variation across the bulk of the potato. In fact, we could neglect all the variations. We could assume that the whole bulk of the potato is at the same temperature. What's happening? Let's, in a different context, in the case of a parallel plate, one-dimensional flow, we notice that the Bayer number is 1. There is the temperature variation within the solid, within the potato, and within the fluid of the same order. But if the Bayer number is very small, that is 1 over Bayer number is large, the variations within the potatoes are small and negligible compared to the variation of temperature in the fluid. So we are not going to make serious mistakes if we assume the temperature throughout the bulk of the potato to be constant, only one temperature. This is the other case when Bayer number is very large. All the variations are within the potato. There is hardly any variation in the fluid. So this problem can be solved by changing the boundary conditions, that the temperature Tf is not in the fluid far away, but it is the temperature at the surface of the potato itself. So the convective boundary conditions can be dropped, and it can be assumed that the temperature at the surface of potato is always Tf. Typical heat transfer coefficients of domestic ovens set at 180 degrees centigrade is of the order of 25 watt per meter square K. The conductivity of potato is between 0.545 to 0.957 depending upon the water content within the potato, depending upon how old the potato is, how long it has been stored. Let's take it as 0.8, a typical value. And let's take the diameter of the potato to be 4 centimeters, a rather small potato. Then the Bayer number is of order 1.2. The Bayer number is order 1. And so the Bayer number would be important. We could neither make the assumption Bayer number is very small and assume the temperature throughout the potato will be constant, nor we can assume that the temperature variation within the bath are negligible, and we can transfer the temperature Tf to the surface of potato. So we'll have to use the Heisel charts. We'll continue with discussion on approximations in the next lecture as well. Thank you.